All right, everybody right now? Cool. So my talk is, probably shouldn't leave the microphone. My talk is about cloud native applications. So in this talk, we're going to go into certain aspects of developing and running a cloud native application, and what does that mean. So my theory is that there has never been a better time to build, deploy, and run and monitor applications using open source software. Does anybody object that? Nope? Sounds great. So, a little bit about myself. Probably should wait for micing up. Oh, all right, this is good. This is better. So a little bit about myself. I'm a software engineer at Google Cloud right now. I work on Kubernetes and container engine projects. My job is to improve the developer experience and figure out what's working, what's not working before a feature goes out, ideally. Before that, I worked at Microsoft Azure. My job was there to work on Docker. If you ever end up typing docker.exe, that was me who started that. I worked on Azure Container Registry and official ASP.NET image for Microsoft as well. And then I developed the official .NET client library for Docker. You can find me on Twitter right here. So before I go on defining what is cloud native mean, I guess I'm going to start with this concept called Google infrastructure for everyone else. So Google, once you just join Google, it's been 7 months for me, so not very long. I've been at Google for 7 months. And the way I observe things to work is wildly different than any company out there. The way Google does things is completely different than how anyone else is doing it out there. So what happened in the past few years is that many engineers from Google left Google. They went to other companies, and they realized, oh my God, I want my tools at Google back, right? So what they ended up doing is they created similar tools. Similarly, companies like Google, like Facebook, Microsoft, Amazon, they started to open source some of their tooling. And pretty much, Google has been releasing a lot of papers. Like if you think about it, the Hadoop project came out of the MapReduce paper, which was just a research paper that came out of Google. So recently, in the past few years, we've seen that a lot of projects in the open source are helping developers like you guys to figure out how to run applications at scale. And ideas for these projects came out of Google. So the next thing I'm going to talk about, I'm still not going to talk about cloud native. But there's this thing called Cloud Native Computing Foundation. The way it works is, in 2015, after Google started developing Kubernetes, Google basically realized we don't want to own Kubernetes. Because if we own Kubernetes, everybody's going to think that this is a Google project. Like, Google doesn't have a perfect, I guess, reputation of keeping projects around, like Google Reader. But still, the way to make a world where the developers are successfully running these infrastructure projects is to actually donate them to a foundation. Similarly, there has been Apache Foundation in the past. Like, there's been Apache Hadoop and so on. So Cloud Native Computing Foundation is very similar to that. It basically started with Kubernetes. Then many other companies joined, like CoreOS, eBay, Twitter, GitHub now. Like, there are so many, probably over 100 members of Cloud Native Computing Foundation. So some of the cloud native computing projects, if you're familiar, they're like Kubernetes, gRPC, Fluentd, Containerd, which actually powers Docker right now, and then Rocket Container Runtime. So what I want to talk in this particular presentation is what goes into making of a cloud native application. So I'm going to start with runtime packaging, and then I'm going to talk about cluster management, topics like RPC, networking, application identity, observability, and service broker, which is a new concept, and CI/CD. So let's start with application runtime and packaging. Who here is not using Docker? 1, 2, 3. OK, that's great. So the reason why microservices revolution happened is because somebody not because somebody came up with it, it's because it was basically a natural evolution. Google has been always using microservices internally. And the reason for that is because, well, guess what? Multiple teams are developing multiple software, right? You can't have them all working on the same project simultaneously. So what happened was there was a natural separation. And the reason was you're developing these things independently, and you're scaling them independently. Like each one of them have separate needs. If you put 20 responsibilities into one application, it's not going to work as smoothly because one part of the application is going to use too much memory, whereas the other parts are not really. So when the application crashes due to a memory leak, the other parts are going to be impacted too. So we're basically separating services that have different responsibilities into separate microservices. And when they crash independently, you're actually in less trouble. So Docker came up with this brilliant idea of using Linux containers, which has been a technology out there, mostly contributed by companies like Google, IBM, Red Hat, into the Linux kernel. So Docker came up with a neat format that you can package your applications in and then deliver it to your machines. So the way it works so smoothly is because it's portable, meaning it works the same way on your laptop as well as on your cloud machine, and it's atomic, meaning a container is either running or not, and if you have an image there, it means the image is completely pulled or not pulled. So when you delete the image, you're deleting the entire image or nothing. So basically, it's like you're not leaving lots of garbage behind you. So right now, part of CNCF, there's Containerd and Rocket projects. These are basically the foundations of container runtimes, and everything is pretty much built on top of these technologies. So the next thing is dynamic scheduling. This actually made a lot of things possible. Prior to that, you all probably know that there's been Kubernetes folks here, that applications used to be deployed onto machines one by one, right? So right now, we're in a world of dynamic scheduling. So if you're running on a machine, a more important job, a more important container can come in and kick your less important task out. That's a really fundamental concept you should be thinking about. Like if you think about how Google works internally, there is probably millions of machines out there, and then inside these machines there are running containers, and some of the containers are deployed by me, and they're not very important. Some of them are deployed by Google Maps, and they're more important. So what's gonna happen is that we just gotta make sure these containers are running somewhere, and they're running happily. As long as that's not the case, we have to move them somewhere else that they can be happy. So I guess the smoothest transition is the cluster management. And I'm not going to go into which container orchestrator or which cluster manager is better. I'm just going to go into what Kubernetes gives you. So first, dynamically manage infrastructure. Basically, what this means is that you have nodes. In the future, you're going to have more nodes, right? Your network topology may change. Every time you make those changes, it shouldn't be necessary that you should go in and make tons of new configuration. And nodes die. Sometimes you get rid of the old CPU that you have. And so all these things basically lead to a dynamically managed infrastructure. The job of the application developer is to not worry about those, right? So Kubernetes gives a smooth separation layer. Application developer is up there. They can still run their applications, but they don't necessarily worry about the machine underneath. So the next thing is the declarative application management. This is probably the best gift of Kubernetes to the world. When you're running your application, you can say Docker run, which is going to imperatively run that container in Docker instance, right? But the Kubernetes way to do things is to actually have a file describing what is your application, how much memory it needs, or what is the image, and then how do you check the health, how do you check the readiness, so these sort of topics. So if you think about this question, can an intern deploy your application stack easily? This probably will give you an idea about how much declarative infrastructure you're doing. If an intern can deploy your application easily, if it takes them weeks, which it did for me back in the day, it's probably you probably don't have an ideal infrastructure going on. So Kubernetes comes in and solves all these problems elegantly, and today it's production ready. So there's not a lot of discussion around what you should be using, although there are other container orchestrators which might be perfectly solving your problem, right? So it's not a battle. I don't see this as a battle at all. Whatever works for you, you should use it. But the way Kubernetes provides the primitives are, I think it's an elegant solution to the problem that's been out there since forever. So if you're not familiar with Kubernetes at all, I'm just going to show you some random application here. This is a guestbook application I have, let's say. The way it works is I have a YAML file here. And when I give this file to Kubernetes, Kubernetes is just going to make sure that this is what's running in my cluster, not anything else. The way it does is, first I say I have a deployment called guestbook, and then I specify labels. This is an interesting concept that came out of Google. So why don't we label everything, right? I can say, oh, this is production. Oh, this is like guestbook application. If I have a load balancer, I can say, oh, this load balancer also belongs to a guestbook application. So this idea, you can take this idea really further, and this is pretty much how Google manages the infrastructure internally. Everything has labels. Unless you're not labeling, you're going to start losing track of your resources. So below there, I have the container image, obviously, and I declare a container port, which is port 80 for my application. And then last but not least, I have the replicas tree. This is really important, because what you can do with this file is you can check this file into your Git repository. And then you can change the tree to 5, and then deploy the same thing to the Kubernetes cluster again. Now you know what's the actual running state of the cluster is coming from in terms of the Git commit. You can go back to a previous Git commit and deploy that, and you're going to get that particular state of the cluster. So why Kubernetes? It's mostly because Kubernetes is really easy to use, although sometimes can be hard to install if you're doing it on your own. So Kubernetes gives you free service discovery using kubedns. You can just say HTTP guestbook, and you're going to reach the service, no longer worrying about IP addresses and ports and so on. And if you have a YAML file that works on your machine, it's going to work pretty much the same way on the cloud, right? You're basically taking YAML files from your computer and then putting them on the cloud. So same application is running both places the same way. I actually heard this many times, that people are really happy that running an application locally on Minikube and taking it to a real Kubernetes cluster usually takes pretty short time. So, and Kubernetes is production ready. It's been out there for a very long time. And I work on Google Container Engine, so I'm obviously biased, but I think Google Container Engine is a really good place to run your Kubernetes workloads. It's mostly because anything goes wrong in your cluster, you don't worry about fixing that yourself. Google engineers are waking up, and they're supposed to fix your problem for you. So the next thing I'm going to talk about is continuous integration. So if you ask yourself, who here is still manually deploying applications? Like you run a command, you deploy. It's OK. You can raise your hand. I do that. It's fine. So if you're spending your time on deploying applications one by one manually, you're probably not making your time worth. Like you're getting paid a lot, but you're spending your time on things that machines can do, right? So I don't have strong opinions in this area, but you should have a CI/CD tool. So particularly, something that came out recently was Spinnaker. And I think the power of Spinnaker is it came out on Netflix, and it has strong primitives. Although it's coming from a VM world, it has good ideas, such as you can deploy a new version of your application and have 10% of the traffic come here, and 90% of the traffic go to your old version. So you can do canary deployments and many other things, actually. It has a pretty complex pipeline machine. Also, another thing to keep in mind is, are your deployments repeatable? Can you deploy the same thing twice, or can you go back and deploy the same old thing before? Like if you don't have this ability to roll back and have repeatable deployments, you're basically signing up for trouble. Because something is going to go wrong, and when something goes wrong, instead of rolling forward, your on-call person who's awake at night or something, they're trying to roll back. So you better have a rollback option. Right? The rollbacks are seriously important. Not a lot of companies in the industry actually practice this, including some of the companies that we worked with before. Rollback is seriously important. And if you don't have a rollback strategy, then you're probably not targeting for very high availability. So the next thing I'm going to talk about is microservices networking. And when I say microservices networking, I'm hoping to talk about less boring and kind of new stuff. Who here has heard of service mesh before? Service mesh. Anyone heard of service mesh? Can't be just one. Come on. OK. So service mesh is a really new concept. What the hell is service mesh? So your application's traffic is basically going through some proxy that knows about your networking details, such as maybe you want to have retry policies. Like there is a service A and there's a service B, right? A wants to connect to B. So what is the retry policy, for instance? If A cannot talk to the B, how should it retry? Right? Normally what we do is we write the retry logic in the application. So is that really the greatest idea? Like what if it was configurable and it was out of your application and it was cluster-wide? Like all the microservices in the cluster are enforcing the same routing policies, same retry policies, same access control, and so on. So what Service Mesh does for you is you don't change your application code. Everything works out of the box. It's kind of like magic. So the way, right now, there are two prominent projects in the area. One is Linkerd, and the other one is Istio. Both are open source. You can try these out. Although they're somewhat mature, they're not really probably for production use right away. Actually, some of these projects came out of companies like, with partnership companies like IBM, Lyft, and so on. So interesting thing is, who here actually encrypts the networking between two microservices? Who here encrypts like TLS between service A and service B? Not many, right? So if you actually start using one of those projects, you can get encryption for free. Like your microservices networking will be encrypted out of the box with TLS. And you can further add like authorization and like basically prevent service A from calling into service B. So there's that too. And you can do lots of other interesting ideas. The way this works is you have a pod and you have another pod. Pod is like multiple containers in a single deployable unit. You can think of it that way, or basically just think of it as two containers. So when app 1 is trying to call into app 2, it basically normally, if you're using Kubernetes or something like that, it directly calls into that application. What we do is we add a sidecar proxy, which means these two, the proxies, are deployed on the side whenever the app 1 or app 2 gets deployed. So what happens is that the app 1 and proxy are talking to each other using localhost, so that's secure. But proxy to other proxy, it's basically TLS communication. So Service Mesh can get you that. And these are often in separate machines, right? So when you're going from one machine to other machine, TLS is really important. That's where the network usually gets intercepted, right? So the next thing is I'm actually going to talk about how Istio works, one of the Service Mesh projects. What we got here is two applications, and they're using a proxy called Envoy, which came out of Lyft. So there is an external component that basically enforces all your networking rules. And this is the Istio pilot. You can put your rules in there. You can put your network policies. You can put your timeouts in there. And every single microservice in your cluster are going to use these. The way this works is basically the Envoy proxy sidecar is periodically syncing with the Istio pilot. So they're separate control planes where you still deploy your application, but you configure a separate component. Am I going too fast? Let me quickly check that. No, we're OK. All right, so the next thing is I want to talk about RPC. Who here is actually not using HTTP to talk between two services? SOAP, SDL, that's all OK. OK, only a few people. I'm suspicious that people are not raising up hands normally too. OK. Anyway, so what is RPC? RPC is remote procedure call, right? So if you're using HTTP APIs, you probably should not use HTTP APIs because that's really not a good thing to do. And the reason I say that is because HTTP APIs are error-proof. Like basically, you can write a field, you can make a typo in a field, and you will not know it until when it fails. So there is no validation whatsoever. Basically, if you're writing APIs using JSON or XML yourself, you're probably doing it kind of wrong until it breaks. So what Google did is back in 2001, internally Google developed this thing called protocol buffers. And protocol buffers is a binary protocol, meaning you can't actually read it. It's like you're loading a video from the internet. It's like a binary format. You're not supposed to read it yourself. But there's serialization and deserialization at both ends of the services, so it works fine. So this is open sourced in 2008. I'm going to show how it actually looks like. But before going into that, I want to say everything inside Google is protocol buffers. So when you type www.google.com, what's happening is that everything inside Google is when you hit the load balancer in the front of Google, the HTTP request gets converted into a protocol buffer request. And then from there on, everything inside Google is protocol buffers. Like imagine there are like tens of hundreds of thousands of Google services internally, and they're all talking to each other using protocol buffers. Because protocol buffers are efficient. You don't make any errors. You generate code for the clients and servers. I'm going to come to that. And then everything is like, it's compressed. So it's not like you're not wasting enough. You're wasting bandwidth on making API calls. So gRPC is a new project that's using protocol buffers primarily. And what gRPC gives you an easy client and side call generation. So if you're writing an API, you'll get the generated code for free. That's what it gets you, and that's why you're not making errors trying to write your API. So this is used by many open source projects and many other companies outside. And example protocol buffers basically looks like this. It's just a text file. It's saying, I have a service called user service, and it has a method called getUser. And the getUser method takes a user request and returns a user reply. And then the user request is basically either you provide an ID and you say whether to include user's details or not. That's that. So the user reply is ID, username, and email. That's the response, right? When you compile this proto file, you get generated code. Basically, you're getting the user services server implementation and a user service client, which is a client implementation. And these servers and clients can be in different languages. One of them can be Objective-C. So if you're writing iPhone apps, you can actually use that. And the other one can be a Java server, Go server, Python server, pretty much anything. And this gives you compile time safety, which is really important. Like you're basically, if you're mistyping field names, you're getting compilation errors. That's the good part. So next thing that I'm going to talk about is observability. So who here is collecting logs from application? All right, everybody is collecting logs. Logs are great. But what's great is other stuff. So if you're imagining at Google, nobody's got time to read the logs, right? No engineer at Google is like taking time to go through the logs and like actually figure out what's important and what's not. So if you have a service and you're not observing it, it means it's not running correctly, period. You may think it's running correctly. You may think that you go to the website, it's running fine, but you actually have no idea whether that application is actually getting slower over time or that application is just like leaking memory until it breaks. Do you want to know when it breaks, or do you want to know before? That's the whole point of observability. So there are several ways to add observability into your applications, and I'm going to go through only a couple of them. So first is Blackbox Monitoring. This is pretty much what everybody is doing. You're basically installing a software on your computer, and you're collecting metrics like how much CPU or memory my application is using. So why is it called Blackbox? Because your application is not giving it. It's already there. You're treating your application as if it's a black box. You can't see what's inside, but you're seeing that it's using CPU and memory, right? So that's Blackbox Monitoring. Also, if you're going to a website, it's also Blackbox Monitoring too. Like you're actually querying the website or the API, that's Blackbox Monitoring. So the next one is a rather new concept, white box monitoring. So this is where the application provides metrics to a daemon that collects them externally. So there are two types of metrics. One type is counters. Counters only go up, right? Like 1, 2, 3. Gauges are more like it can change depending on the time. Right now, your memory usage might be 300 megs. A couple hours later, it might be a gigabyte, right? So there is that. So the metrics can be aggregated. And when you aggregate the metrics, you actually get really valuable information, such as what is the CPU usage in all my applications in this particular region? Or for how many requests did this front end handle and instances of this particular version? So you can get really interesting metrics out of your application. And I'm actually going to show some of them. So the next thing is Prometheus I'm going to talk about. And the Prometheus is another CNCF project, another Cloud Native Computing Foundation project. And it's pretty much the de facto solution to expose metrics from your application. What does actually these two give you? Sorry, wrong slide. So the next thing is also tracing. Totally forgot about that one. Who here is actually tracing stuff? That's really interesting. One person, you're great, sir. So the next thing is tracing. The way to trace things is you're basically adding things into your application code. You're saying, oh, I'm just going to call this function something. And then the next thing is you're creating all these monitoring labels inside your application, which is collected by somebody else. So what happens is that when a request comes to your website, you know exactly what time is spent on each particular microservice. Even more detailed, you can go into a microservice and see which method is taking the longer time. This is really useful. Actually, a lot of companies like Uber, Lyft, and internal, actually this came out of Google too. There's a paper called Dapper. It got implemented later on, and then Twitter implemented Zipkin. So there are multiple projects also in this space, Jaeger, Zipkin. What they're all doing is they're giving more visibility into where the time is spent in your application. And I'm going to show an example of that too. So this is the first example, white box metrics. Imagine you have a service, and somebody is going to call your service like that, /metrics. This is Prometheus. And the format is roughly this. I got this many HTTP requests. I got this many errors since I started, right? And then I got this many threads right now. And I've been up for this many minutes, and so on. What you can find here is that, imagine you're collecting this info from all your instances. You can answer questions like, how many users signed up in the past 1 hour, right? Because every time this service, this my service, handles a registration, the accounts created is going to increase by 1. You can just write this yourself. This is a really simple format. So the good part of this is you can get super close, like super short, delayed monitoring into your applications. Because collecting these info is really cheap and simple. At Google, we basically detect stuff like solar explosions because the error correction bit in machines go up, and like we suddenly see a tick in all the machines that we have because the error correction happens. So it's like you can get really, really detailed stuff if you collect all the metrics. Like at any application running at Google, we probably collect like over multiple hundred metrics. So there's that. Some of the metrics you can get out of the box, like if you're using gRPC, you may have it automatically plugged and show you how many RPC requests this application has sent and how many of them took in average and so on. So this is an example trace. If you have never seen a trace before, this is basically like a waterfall. So this is saying that there was a request on the top. This is, by the way, Google Stack driver. And this is showing you that there is a request on top. And it's saying that it took about 7 seconds. So it can basically tell you how many, where the time is actually spent inside your application. So here I see that, oh, there was this method, and then it went to this method, and then it went to this method. So these methods kind of ran in parallel. This was OK. I guess somebody parallelized these. So you can basically see what's taking time, and you can optimize based on that. So this is another view. It's from Ivers Jaeger. It's not really interesting. So application identity is the next topic. So what application identity is that? Can you accurately identify and block the traffic in your microservices? Like, can you tell if a request is coming from service A or some other random service or somebody who got into your cluster and hacking your stuff? So this is basically what authentication and authorization means. If you can't find out who's sending you the request, it means you don't have application identity. Simple as that. And when somebody sends you a request, can you verify that somebody stole their credentials or not, if they're impersonating the request, and so on. So this is the in-cluster traffic security that I want to talk about. So if you're using JWT, you're probably getting this for free. If you're not using JWT, you're probably implementing something that yourself. You probably should not be implementing that. Please don't invent your own crypto or anything like that. If you're using Istio that I talked about earlier, you get cluster identity for free. So every application has an identity. It has a name, so you know where each request is coming from. And you can block them. That's the most important part. Also, the authorization. If you're not blocking who's coming from, means that you're not like any service can call into any service. That's a security problem, OK? Well, I know many people don't care about it in most use cases, but it's a big deal. OK, so the next thing I want to talk about is service brokers. This is really new. Not a lot of people are using service brokers right now. So service brokers are, basically, there's this concept called Open Service Broker API. If you don't know what a broker is, it means you're getting something from someone and giving it to somebody else. And the way service brokers work is you have a service, and you need a resource, like a database, right? How does your application get the database? Ideally, somebody goes to, I don't know, a cloud provider or does something manually to create a database, right? What if we can automate that? What if you can say, I have an application which is the guest book, and I want a MySQL database with that? That would be cool, right? So right now, this is the service broker work is pretty much like it's happening, and it's you can say like, give me a MySQL database, and you can have the password delivered to your application as well, which is really cool. Or maybe you want only a storage bucket for your application on the cloud providers like Google or AWS. So this is basically the service broker concept. The way it works is there's a service broker which is giving you the resources. Like you can write a piece of software that gives you MySQL database. The next thing is you have a service instance, meaning you want a SQL database. The third thing is you have a service instance by them. You're saying, I want a database, and I want this database password to go to this application. And service catalog is basically orchestrating this whole thing. This is a really new concept, but I'm guessing that in the enterprise world, this is going to take off really quick. This idea actually came out of Cloud Foundry. It's not original. But I'm going to talk about how Kubernetes Service Catalog looks like, which is pretty much similar. So here, I have a broker. I say that anytime you want MySQL, basically go here. So the API is something that the service, open service catalog API knows about. The next thing is, I have a manifest file here again. I'm saying I want a guestbook database. And I want to call it MySQL database. Sorry, I want to call it guestbook database. And it's a MySQL database, and I want it to be small, right? So next thing, I create a binding. I basically say, I want to basically take that guestbook DB application and create a binding out of that. So this is basically creating the database password into a Kubernetes secret. So this is pretty much what I was going to talk about. If you have time, I'm hoping to take questions. I hope that this really gave you a basic picture of what's going on in a modern application, which we call cloud native. So cloud native is not how your banks deploy software most of the time, how your college departments deploy software. So this is a new revolution that's happening. It's happening organically and naturally. I wanted to just highlight, go into these parts, and see what is the cutting edge technologies, what's really modern, ideally how you should be doing. If not, you really don't have to use any of the things I mentioned here, but I'm hoping that these give you some perspective. So this is pretty much my talk. If you have any questions, I can take it right now or after in the open space sessions later on. Thanks.